Questions 21 through 25 on the 2017 Grade 10 Cayley Math Contest. The integers 1 to 6 are to be inserted into the grid shown. No two integers that differ by 1 may be in squares that share an edge. If the 1 is inserted as shown, how many different integers can be placed in the box labeled x? All right, well, let's just work this out. Trial and error, basically. Not much more than that. Okay, so here's the numbers. 1 is always selected, so here we go. Let's say the next number is, I can't put a 2 in here because that violates the rule. No two integers that differ by 1 may be in squares that share an edge. Okay, can't put a 2. Let's start with the 3 then. If I put a 3 here, well, I can't put a 4 or a 5 there. I can't put a 2 or a 4 there, right? Those are the rules. So I put a 5 here, and then I put 6 there. And here, I can't put a 4, so I can put a 2, and therefore the x becomes a 4. All right, so let's just put 4 here as the possible choices, or possible result for x. So this is basically what you have to do. You just have to keep doing trial and error. There really isn't much more than that. So I tried 3 as my next one. That didn't give me any problem. So let's try 4. 4 is my next one. If I put 4 here, I can't put 5 or 3, but I can put 2 or 6. So I'll put 2 here, and therefore 6 here. And that means here I can't put a 3 and I can't put a 5, but those are the only options I have left. So this results in nothing. All right, next one, 5. So I'll put a 5 here. Okay. I can't put 6 or a 4. I can only put 2 or 3. So I put the 2 here, 3 here. And then I can't put a 4. So the only one that can go here is 6. And therefore x is 4 again. All right. So that's fine. And now we go to 6. So 6 goes here. I can't put a 5, but I can put either 2, a 3, or a 4. So I've got several choices here. Let's try the 4. If I put a 4 here, I'll put a 3 there. Why not? And then I get stuck because if I put a 5, that doesn't work. I put a 2, that doesn't work. Okay, so that wasn't helpful. If I put a 4 here, let's put a 2 there. If I put a 4 and a 2, then the only numbers left are 5 and 3, and neither of those can go there. All right, so moving right along. Let's try a 4. Well, I already tried the 4, so let's try 3 and 2. If I put 3 and 2, the only number that can go here is 5, and then I get 4 again. So I think I've exhausted everything. I've tried all the different ways, and the only one that I kept coming up with for x is 4. So there's only one possible integer that can go in the box labeled x, and therefore number 21, the answer is 8. In the diagram, square PQRS has side length 42 and is divided into 4 non-overlapping rectangles. In each of these 4 rectangles has the same perimeter. What is the area of the shaded region? Let's label some things now. X, 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 Y, Z, and then this would be 42 minus X, and this will be 42, obviously. And I think that's good enough for now, 42. Let's concentrate on these 2 boxes first, and let's see what we get. So the perimeter for those 2 would be 2x plus 2y, and the other one would be 2x plus 2z. Now both of those are equal, so that means 2y is equal to 2z, and therefore y is equal to z. Okay? So that means this guy from there to there would be 42 minus 2y. And that's also 42 minus 2y. And therefore this distance from there to there would be just 2y actually. All right. So now let's figure out the equations of the 4 perimeters. So the first perimeter was this guy. The second perimeter was that. The third perimeter, if we look at this rectangle, that would be 2 times 42 plus 2 times 42 minus 2y. So that's going to be 84 plus 84, so that's 168 minus 4y. And we'll call that triangle or rectangle 3. And this is 1 and this was 2. And then the last one, the fourth one, is this one. That perimeter, we'll call it 4, is 2 times 42 minus x plus 2 times 2y. And that would be 84 minus 2x plus 4y. Okay, so now we have to obviously equate a bunch of these. So where do you want to begin here? We can say it doesn't really matter. That one is equal to this one. I think that will help. Okay. There's lots of ways at this point, but any way that you'd like to do it is fine. 84 minus 2x is equal to 2x plus 2y. And then that means that 2y is equal to 2y plus 84, that is equal to 4x. And then dividing through by 2, you get y is equal to 2x minus 42. And then now I can just substitute. I'll use this one now, that one, and this one, since they have x's and y's. So 168 minus 4y is equal to 2x plus 2y. And then now I can substitute for y. So 168 minus 4 times 2x minus 42 is equal to 2x plus 2 times 2x minus 42. So this becomes 168 minus 8x minus or plus 168. And then this is 2x plus 4x minus 84. Put all the x's on one side, and that's going to be 14x. And then these numbers all add up to 420. And therefore, x is equal to 30. There we can substitute back into there to get the value for y. That's going to be 60 minus 42, 18. And then now we can calculate the area of the shaded region. The area of the shaded region up there is just x times y. X is 30, y is 18, and therefore that is equal to 540. Number 22, the answer is E. The triangle with side lengths 6, 8, and 10 is right angled, while the triangle with side lengths 6, 8, and 9 is acute angle, and the triangle with side lengths 6, 8, 11 has an obtuse angle. An obtuse triangle with positive area has side lengths 10, 17, and x. If x is an integer, what is the sum of all possible values of x? Well, first thing, of course, is the triangle inequality. And that one tells us that 10 plus 17 has to be greater than x. So that means x is less than 27. It also tells us that 10 plus x has to be greater than 17. So x has to be greater than 7. So from this, we know that x is going to be greater than 7 but less than 27. Now, do we just add up all of those and call it a day? And the answer is no. This is a reference, but not everything in there will be valid. We have to figure out which ones are going to indeed work with our conditions of something in particular that's very important, that it has to be an obtuse triangle. Okay, well, let's create a couple triangles and off we go. So the first one, we'll just draw a little triangle here. This is a right triangle. Now that's going to be important for me because it's going to give me a reference. So if I call this 17 and 10 and x, if it's a right angle, 17 squared plus 10 squared will be equal to x squared. So that means x squared will be equal to 389, and therefore x will be approximately 19.72 if it's a right angle. But we don't want right, we want obtuse. So this angle, we want it to be a little bit bigger. So that means we would like it to kind of extend like this. Now, that means that x has to be greater than 19.72. That's the only way that we're going to be able to make this obtuse. And then now we can go back and look at the other end of the inequality, and that is x has to be less than 27. So from this, we can get values for x. And remember, x is an integer. So x will be either 26, 25, 24, 23, 22, 21, and 20. So those are our values. Okay, so far so good. Now we have to look at another scenario. And that other scenario is obviously when x is one of the legs. So the first one we had made x the hypotenuse, but now we have to look at what happens when x is one of the legs. So for example, if this is x. If that is x, then we can put, say, 17 here and 10 here. And this is a right triangle. So let's see what happens when it's right. 10 squared plus x squared is 17 squared. So that means x squared will be 189. And therefore x, when you do that, square root is 13.74. Now we have to figure out if this is going to be obtuse, what's the story? And that takes a little bit of thinking. And when you do that thinking, you get to the conclusion that x has to be less than that in order for this to be obtuse. And go back to the triangle inequality to get the other end of the spectrum, and that's 7. So this inequality tells me that x is either 13, 12, 11, 10, 9, or 8. So there we go. Those are the values, these ones and these ones. And when you add them all up, you get 224. Therefore, number 23, the answer is E. Three coins are placed in the first 3 6 squares as shown. Move consists of moving one coin one space to the right, assuming that the space is empty. No coin can jump over another coin, so the order of the coins will never change. How many different sequences of moves can be used to move 3 coins from the first 3 squares to the last 3 squares? A few things we have to establish. The first thing, of course, is that the number of moves for x, the number of moves is always going to be 1, 2, or 3. And similarly, y, the number of moves is 1, 2, or 3, or 0. And similarly, z. Those are the boundaries. Another very important thing to establish is that if you move something, it has to work in a way so that there's enough empty spaces. So what that means is that if you move z, say 2 spaces, I move here, y cannot move more than that, right? Because y can go here or here, but it can't go 3. So from that particular example, y has to be less than or equal to z in terms of the number of spaces. So the same thing holds true for x also. So from that, we get that x has to be less than or equal to y, which has to be less than or equal to z, which has to be less than or equal to 3, and greater than or equal to 0 for x. All right, so now we're going to define a very important sort of term, and that is s, x, y, z. You say, well, what is this? This is a term used to describe the number of sequences which result when you move x spaces, y spaces, and z spaces. So, for example, let's say I said to you, what is S of 1, 0, 0? Well, if you look at that one, that doesn't match that inequality. So this would be 0. You can't make any sequences with that. You can't have Z and Y not move and then have X move, right? If this is 0 and this is 0, that basically means that Y didn't move, Z didn't move. But this is 1, that means that X has moved 1, and that's not possible. So since it's not possible, that is 0. 0 sequences. How about S of 0, 0, 1? Well, that just means that Z moved one space, so it moved here. And therefore, there's only one such way of doing that. So this is 1. So these are just simple examples. This is just a sequence of one move. All right, so what we want to find in this question, our goal is S of 3, 3, 3. That is what we want to find, because that will give me the answer to this question. That will be the number of sequences that result in moving X 3 spaces, Y 3 spaces, and Z 3 spaces. Because at the end, in order to go from here to here, you have to have moved X 3 spaces, Y 3 spaces, and Z 3 spaces. All right, so now that that is established, after you analyze the scenarios, there's a very important and extremely time-saving recursive formula that you can establish. And that is that this Sx plus x, y, z is equal to Sx minus 1, yz, plus S of xy minus 1z, plus S of x, y, z minus 1. If you can establish that, the rest of the question will be very straightforward for you. So, for example, S of 0, or let's try 1, 1, 1. 1, 1, 1. Well, according to this, it's S of 0, 1, 1 plus S of 1, 0, 1 plus S of 1, 1, 0. Okay, well, let's figure this out. S of 0, 1, 1, this one here, that means you've moved Z 1 space and Y 1 space, and that's it. That's all you've done. So there's only one way of doing that. There's only one such sequence. In this case, however, it fails this inequality, this one right here, because X cannot be greater than Y. So this becomes just 0. This one also fails because Y cannot be greater than Z. So that's 0. So this just gives me 1. So that is just one example of that recursive formula. So now let's start by making a table. So in this table, I have set Z to be 1. X are these values, either 0, 1, 2, or 3. And Y is also 0, 1, 2, or 3. So what we do is figure out what is this value. Now this table, the numbers are pretty straightforward because a lot of these fail that inequality, which is up here. That inequality fails for a lot of these. So that's why you see all these zeros. But the only ones for which this works is when you have S of 0, 0, 1, S of 1, 1, 1, and S of 0, 1, 1. Those are the only three this works for, that you can get any sequences, and they're fairly straightforward. These ones you can just calculate in your head without the recursive formula, or without the formula. And that this is just one sequence, this is just one sequence, and this is just one sequence. And That's why you see 1s there. Now what we have to do is insert what happens when z equals 2. So here we go. When z equals 2, you get this table. Now you say, well, how did you figure out these numbers? I can understand the zeros. The zeros exist when the inequality fails, that 0 has to be less than x, which has to be less than or equal to y less than or equal to z. But how did you get these numbers here? Well, this is where that formula came in. So I'll give you some examples. S at 0, 1, 2. Well, according to that formula, it would be S at negative 1, 1, 2 plus S at 0, 0, 2 plus S at 0, 1, 1. Okay, well, this one is 0. You can't have a negative. You can't go in the other direction. And then 0, 0, 2, well, that one, that's straightforward. It's just z moving 2 spaces, so that's just a 1. And then 0, 1, 1, well, that's right here. So that's 1. So therefore, this is equal to 2. So 0, 1, 2, which would be 0 for x, 1 for y, and 2, that would be that. That's why it's a 2. So let's just do one more to kind of show how this formula is working. Let's show how we got S of 1, 1, 2. All right, well, according to this formula, it is equal to S of 0, 1, 2 plus S of 1, 0, 2 plus S of 1, 1, 1. And that is basically 0, 1, 2. We just actually figured that out, is 2, okay, plus S1, 0, 2. Well, this one fails the inequality because x cannot be greater than y, so that's 0. And then S1, 1, 1, that one we got over here. That's just 1. So this is 3. And that's why when x is 1, y is 1, and z is 2, we get 3. So you see how this is being filled out? So that's basically what you have to do. And our goal is to get 3, 3, 3. And when you keep using this formula to fill out the table, you will eventually get this S333. Here's z equals 3. Here's x equals 3, y equals 3. And as you can see, that number is 42. So it's a challenging question. It's a difficult question. And I encourage you to understand why that formula works. And therefore, number 24, the answer was 42, and that's choice C. A positive integer n with n greater than 3 is called a Nella number if there exists a positive integer x with x less than n, and there exists a positive integer m such that m is not divisible by x or by x plus 1, and m is divisible by every other positive integer between 1 and n inclusive. For example, n equals 7 is a Nella number. How many Nella numbers n are there with n between 50 and 2017 inclusive? First thing is, let's try to understand why n equals 7 is indeed a Nella number. Well, we have to look at all the integers that are in that range from 1 to n inclusive. And then we have to try to figure out an m such that when you divide it by every number in that range, it's going to result in an integer except x and x plus 1. Okay, so that basically means that m divided by x is a no in terms of divisibility. M divided by x plus 1 is a no. But m divided by all of the other integers, all other from 1 to n inclusive, that is a yes. Okay, Well, it sounds to me like there's a lot of prime factorization going to be done in this question. That's going to be 2 times 2, 2 times 3. So we have to fiddle around with this. Okay? And after you put some thought, you come to the conclusion that if m is equal to 42 and x is equal to 4, this is going to be y. This is an Ellen number. So for example, m is 42, right? So 42 divided by 4. That is a no. It's not divisible. How about m divided by x plus 1? 42 divided by 5 is also a no. But 42 can be divided by all the other guys, which are 1, 2, 3, 6, and 7. So basically, we had to find the least common multiple of 1, 2, 3, 6, 7. And that was how I got 42. It was basically the LCM, which is 2 times 3 times 7, which is 42. Least common multiple. All right, so I hope that makes sense. You have to understand the question before we actually tackle this whole big monster there. So when you, after some analysis, you can conclude 2 very important rules. The first rule is that x and x plus 1 are going to be either a power of 2 or a power of a prime. So either they're going to be powers of 2 or the power of a prime. So for example, in our little scenario up here, if you noticed x was equal to 4, which is indeed a power of 2, it's 2 squared, and x plus 1 was 5, which is a power of a prime. Well, it's just 5 to the power of 1. The second conclusion is that n is smaller than the next power of 2, because they told you in the question that x is less than n. So for example, x in our little scenario up here was 4, and that's got to be less than 7, which is what n was up here. And obviously n is smaller than the next power of 2. The next power of 2 would be 2 to the power of 3, since that was 2 to the power of 2, and 2 to the power of 3 is 8. So this inequality must hold true. And these are the 2 rules that we need to abide by to solve this question. So now we have to create a table and look at all the values of n from 50 to 2017 inclusive, and keeping in mind that these rules will help us narrow it down. So here's the values of n all the way broken down by powers of 2, right? 2 to the power of something has to be the endpoint of the range. And then n, as we have said, has to be smaller than the next power of 2. So the largest power of 2 less than n is listed here in this column. And then we have listed x and x plus 1 because x has to be less than n, and x and x plus 1 obviously are consecutive integers. And in this scenario, we have made x a power of 2, so 2 to the power of something, and then x plus 1 is just the number after it. In the other scenario, we'll make x plus 1 the power of 2, and so on. So if you look at this table, we have to conclude that does this work or not? If x is a power of 2, well, that's how we made it. That's no problem. But what about x plus 1? X plus 1 has to be a power of a prime. One has to be a power of 2. The other has to be a power of a prime. Which ones are a power of prime? This one is not a prime. Neither is this one, neither is this one. This one is a prime. This one is not. This one is not. So the only scenario in which x is a power of 2 and x plus 1 is the power of a prime, say q to the power of something, where q is a prime number, is this one. So this is the only range that we have to be concerned with. All the others fail. So all of these guys fail here. Okay, so 257 is less than n is less than 512. And for all of these, we have to see if we can find some m that when you divide it by 256, this guy, which is x, and when you divide it by 257, which is x plus 1, it is not divisible. So no and no. But it is divisible by every other n, from 1 to all the way up until n, inclusive. So when we look at that, we realize the following, that 512 obviously has to go, because if 512 is n, then that means that m would have 512 in it. And if m contains 512, then this would be divisible. 512 divided by 256 is 2. So that one goes. And therefore, n is going to be between 511 and 257. Those are the only ones. So all these integers will be valid. So that's what, 511 minus 256. And that is equal to 255. So that is the first of the values. So we got 255. Now we want to create the same table again, but this time reversing x and x plus 1. So here we go. The ranges are the same, but this time we're looking at the powers of 2 as x plus 1. So this time these are 2 to the power of whatever, p, let's say. And therefore, we have to see if this is a prime or not. Is it some prime q to the power of something? Okay, when we look at these numbers, this is a prime, and that's it. Those are the only two. So that means we are only going to be concerned with that range and that range. Looking at the first range, n is between 50 and 63. Okay, well, first of all, how many numbers are there? 63 minus 49, that's 14. Okay, now all of these valid. Well, in order for them to be valid, m divided by x plus x, which is 31, and m divided by 32, some m. This is a no and this is a no, not divisible. But m divided by all the other guys, all other, from 1 to n inclusive, that would be a yes in terms of divisibility. Okay, well, most of these 14 are okay, but there's two that are not. And those are 62 and 63. And let me explain why. These cannot be Nella numbers, not Nella. And the reason is because if you were to make them Nella numbers, then the m that you create would contain 62. For example, if it's 62, 62 would be part of the product. The only thing that's not part of the product is the x and x plus 1, correct? So 32 and 31 are the only two that are not. So m would contain 62. If n is equal to 62 or 63. And if that's the case, then this m would be divisible by 31, since there's 62 would be in there somewhere in that product, and of course that's not allowed. So we have to subtract these two from this 14. So the total number is actually 14 minus that 2, which is 12. So 12 is the answer to that. Now we get to our final scenario, which is this guy, which is n is between 128 and 255. Well, how many numbers are there? 255 minus 127, and that's 128. Okay, now are all of these valid? And the answer is no, because when n is equal to 254 or 255, that's going to be a problem, because our m cannot be divisible by x, which in this case is 127, right here, and our m cannot be divisible by 128, right there. But if n equals 254 or 255, m would contain 254. And therefore this would become divisible. So that's a problem. So from this 128, we actually have to subtract these two guys. So it'd be 128 minus 2 is at the actual number, and that is 126. So there we go. We got this 255, we got this 12, and we got this 126. So 255 plus 12 plus 126, and that is 393 for this very challenging question, and that would mean the answer for number 25 is A.